Nadia. Okay, let me click on, got it. Well, thank you, Nadia, for the introduction, and also thank you for the invitation. I'm going to wish you, I hope you have a nice afternoon. For me, it's morning. This is a work that I've done in collaboration with Clément Vela. Vela is a student at the ENS, École Normale Supérieure de Paris-Saclay. He was actually doing a training with me this year, and actually was able to come to Montreal. Unfortunately, I haven't seen him at all. We did everything online, of course, through Zoom meetings. And I took the liberty to invite him to the seminar, but now he's on the West Coast, so he has it's very early for him. All right. I'm going to talk about the construction of reduced order models. Let me show you the content of the talk. So I'm going to take a very small toy problem, a 1D model problem for the wave equation. At the beginning, I'm going to talk about the classical discretization, and I'm sure for most of you, it's going to be known stuff. My view is to remind you like a few problems when we treat the wave equation. And then I'm going to talk about the Hamiltonian and Lagrangian formalisms. That's going to be necessary to introduce a PGD. And what I will try to convey is, although those two formalisms are equivalent at the continuous level, it creates some little issues, differences, when we do the discretization. And I'm going to then to give you some numerical examples, and this is when you're going to see the small differences, but which are important. And I will finally conclude. This is a work, we got inspiration from this reference that I'm showing below. Let me see, actually. Do you see my my little hand?
Yes, we see.
Okay, so I'm just going to use this. That's going to be simpler. So this is based on essentially this work. They did some space-time PGDs for elastodynamic models, and they had some problems with stability. So in some senses, we revisited this work, and also the point was to make sure that we introduce the formulations at the continuous level. They did the work usually at the discrete level. And since we are interested in doing error estimation, we wanted to formulate the problem first at the continuous level. So here it is. So as I said, this is really a toy problem. We have the wave equation in 1D. Of course, we took the cross-section of 1 to simplify a little bit the equation. So we have rho, our density, E, the modulus of elasticity, and F, a forcing term. So here it's essentially for notation. When I'm going to talk about time derivative, I'm going to use the dot. Sometimes I'm going to use the prime for the derivative with respect to x. And that's about it. Homogeneous boundary conditions. So in most of the problem, we will consider those homogeneous boundary conditions, and we will also introduce some initial conditions. One point I wanted to make, basically, I'm not going to talk about UQ, but the goal here is essentially to construct a reduced model to solve this equation based on the PGD, the proper generalized decomposition, in order, as a tool, to do UQ later on. Okay, so for this in the special case where we have f0, v0, the initial velocity 0, and u0 given by this simple state, basically this is the bar in static subjected to attraction t at the end, we can actually, using the method of separation of variables, we can find the exact solution, which is going actually, and what we see here, and I'm showing this, is essentially that the exact solution is given in as a combination of those modes, modes in x and modes in t. And later on, when we are going to do the PGD, this is going to be our goal, to find on the fly the phi x and the psi t. Okay, so this is the solution. And this is the solution that we get using this analytical formula. Okay, and I hope it's going to work. Oh. Okay. It doesn't want to show the movies. Sorry for this little technical problem. It was working, of course, perfectly fine when I was showing it on my screen. Just a second. All right. It doesn't seem to work. Let me see again. No, it doesn't want to work. So basically, I just wanted to show you the evolution of the solution as we were adding more modes. Unfortunately, it's not working. Yeah, but okay, I have a message from Clément that tells me that it works also in his case, but I don't see how.
Hi, Serge.
Yes.
Here. It might be that it works in full screen, but not in, like if you go full screen, it might work.
Yeah, but it doesn't work actually when I go full screen, it's not going to, you are not going to see it.
If you go full screen first and then share your screen, so go full screen, share on Zoom, and then we'll be able to see the full screen and also see the video.
So let me stop sharing then. I'm going to.
Yeah, so full screen first.
Yeah.
And then
view full screen. But the problem is, like, if I'm sharing, if I'm full screen, I don't see the Zoom.
Just full screen and then Alt tab or Control tab to switch to Zoom.
Okay, Zoom. Okay, thank you. I'm going to get it there. No, it doesn't go.
On my computer, Command Tab let you go through all open windows. Command Tab on Mac.
Got it. I got it.
Mhm.
And now I'm going to share my screen. Thank you. No, but it doesn't show any. It doesn't show it. Okay. So okay, I'm going to do it. I'm very sorry. It still doesn't work. So basically, I wanted to show the different modes and that the solution were converging to some triangles. Here I'm showing the displacement on the left, and along the x-axis it's the time. All right. So now for the weak, so I'm just going to show you the classical discretization of this problem. So we start with a semi-weak formulation. We just do the integration with respect to the space. We here have the problem that we are considering. Then we introduce a finite element formulation. And this is essentially the problem that we get, that we can write in the matrix form as M, where M is going to be our mass matrix, K, the stiffness matrix. And this is the problem that we were trying to solve. Now we are going to introduce a time discretization. And of course, the main objective when we are solving this kind of problem is to ensure that the conservation of energy in the system is preserved. We have a conservation of energy. So first possibility is to introduce a backward Euler scheme. And in order to do that, we introduce a new variable v, and which is simply going to be the derivative of our unknown u. And the backward Euler schemes, basically it's going to give us those equations that we need to solve. And in matrix form, we can simplify the problem. And we just have this system of equations that we need to solve for un+1 and vn+1 and iterate until we're done. So this is the solution that we get. So essentially, after 40 modes, I'm showing here the analytical solution, which is given here. And maybe you see it, we still see some little wiggles in the solution, and wiggles that also we are going to find in the FEM solution. And those wiggles are essentially due to the Gibbs phenomenon because of this shock wave. More important essentially here is when we use this backward Euler scheme, as you may know, is that we are going to lose energy. There's going to be dissipation, and in this case, it's simply numerical dissipation. And I'm showing here the evolution of the total energy that decreases with time. So this is not a scheme that we would like to use. Of course, we know that we need to use some symplectic method. And one possible scheme to do that is to use the Newmark method. And I'm showing here the equations that we need to solve using the Newmark scheme. The system that we obtain basically is going to be very similar to the one we obtained before, with some little differences. The good things, for example, we had A before, now we have this AP matrix, and which is given in term of M and K. And we have also a few little differences. The good things is, of course, that this scheme is going to preserve our energy. Again, I'm showing the analytical solution using 40 modes, and now the solution. And we see that the energy is not dissipated anymore. Of course, we still have some errors, but the energy remains constant. So this is what we want essentially, is to have some methods that are symplectic, that are going to basically preserve our energy. Concerning the spurious oscillations and Gibbs phenomena, we are not too concerned about this. There are methods that can eliminate a part of those oscillations, and I'm giving you a list here. All right. What I would like now to talk about is the two different formalisms, one based on Lagrange and one based on Hamilton. There are some subtleties, and I'm not going to really talk about all those different subtleties. Actually, Clément would be the one to talk with if you are interested in all those details, because he really looked into the details of those formulations. But the idea is the following, and I'm going to start with the Hamiltonian formalism. We are going to consider Q, the generalized coordinate function. And we are going to introduce what we call the Hamiltonian H. And the Hamiltonian H is essentially the kinetic energy, the potential energy, and the external energy. And here I'm writing it in terms of Q, the generalized coordinate, which was essentially the U that we had before, our displacement in this case, and Q dot, the time derivative. Oops. Now, in the Hamiltonian formalism, what we do is to introduce a new variable P, which is simply rho Q dot. And in that case, and we call it the generalized momentum and the conjugate function of Q. And we can rewrite the Hamiltonian in terms of Q and P. And in this case, it's going to be given as such. We have a relation between the Lagrangian L and the Hamiltonian H. It satisfies simply this equation. I'm also going to introduce now the action functional S, which is essentially the integral of the Lagrangian over time. And when I use this definition of the Lagrangian base, this action in terms of H is given as such. What is important here is basically we can use the principle of least action, that we call also the Hamilton's weak principle. And it says that the derivative of this action is going to be equal to this term, which involves the state at T0 and Tf. So using ds, our Gateau derivative of S, we obtain this equation, and I'm not going to go too much into the details, by integration by part to put all the time derivative on our unknown P and Q. So we integrate by part this first term. What we obtain is this equation. And essentially it tells us that Q dot is going to be equal to the first derivative of H with respect to P, and P dot is going to be the negative of the first derivative of H with respect to Q. When I use the definition of the Hamiltonian that I gave before, this is of course the two equations, the equation that we obtain, and we now find that this is going to be dH dP, and here we are going to have dH dQ. What we have essentially is a system of two equations, and here I'm showing the test function in magenta. So we need to satisfy this weak form for every P and this equation for every Q star. So in the Hamiltonian formalism, we do introduce, so now we have a system of two equations. What is nice? I mean, one thing that is nice about this formalism is basically we have some flexibility to introduce the discretization of the two equations. And in this case, what we are going to use essentially finite element not only in space, but also in time. And so I'm showing here some details where we consider the trial function Q and P, given at the linear combinations. And we have also the same for Q, for our test function Q star and P star. So we are going to discretize as usual in space. And I'm considering VH the span of all my basis function phi j. But for the time-dependent coefficients, Qj, Pj, I'm going to consider piecewise linear in time. So for the trial functions, and constant, piecewise constant in time for our test functions. So when we do insert these trial and test functions in the weak formulation, this is the system that we obtain. And there's a slight difference. We need to see that now M bar is not exactly the mass matrix, but it's the mass matrix without basically our density. And M double bar, it's going to be the one when we have actually one overall in this integral. So of course, so that's going to be a little bit different from what we saw earlier when we were using the Newmark method. But now if rho is a constant, then we have this relationship. Moreover, if rho is of course 1, then we are going to get exactly the same system that we obtain when we use the Newmark method. Okay, so here there is still a slight differences with the Newmark, basically with respect to those mass matrices. Now the Lagrangian, it's going to be defined. Now I'm going to introduce the Lagrangian formalism. Basically, the Lagrangian was defined as such. It's almost the same as the Hamiltonian, except for an extra term. And in the Lagrangian formalism, we have only Q and Q dot. We don't introduce a new variable. And we follow the same step as before. We are going to have the action S. We can use the principle of least action. And this is essentially what we are going to obtain. This is the equation that we have. And when we do an integration by parts, to put the secondary, I mean, to have Q dot dot, we can cancel those terms. So essentially, this equation is the one that we were using the classical approach. In some sense, I'm showing that Lagrange is equivalent to Newton. Okay. All right. So now I would like to explain to you why I wanted to introduce this Lagrangian and Hamiltonian formalisms. And it's going to be very important when we are going to consider the PGD decomposition, the PGD method. So I think some of you know what the PGD is. That was introduced by Ladevez in the late 90s, early 2000. And essentially, the method consists in finding an approximation of the solution in the separated form, as I said earlier. So we want to have U given by UCL. So UCL is essentially a lift function that takes care of the boundary conditions. and this combination of modes psi k, phi k. We do a separation, and of course we want simply to truncate to get a good to get an approximation of our solution. So of course, in that case, we need to assume that the solution that we are looking for can be represented as such. Most of the time it's the case. It's not always true for more complicated problems. Anyhow, now what we want to find are those modes on the fly. We want to construct those modes, and we can use a progressive method. Basically, once we know -1, we simply want to find the next mode, psi, phi. And I don't introduce the m to simplify the notation. Okay, so this is essentially, so we could actually look for all the modes at once. That's not efficient. So this is what we use, a progressive method. Okay, if U is known, basically we can find also an approximation of the solution using some kind of an SVD. This is not what I'm interested in. Here I would like to find the solution using a Galerkin method by the Lagrangian formalism, or by a Galerkin method using the Hamiltonian formalism. Okay, so I'm going to start with the Lagrangian formalism. I'm recalling here the equation that we are going to start with. At this point, what we want is to find Qm. Once we know Qm-1, basically we want to find lambda and mu. So I introduce here the notation. Lambda is going to be the mode with respect to the time, and mu with respect to the space. We are going to proceed with a fixed point approach. The problem is when we are going to introduce this into our equation, we get a nonlinear problem. So we are going to use a fixed point approach to find lambda and mu. So first, we are going to solve for mu and assume that we know lambda. And then we solve for lambda with mu known. Basically, this is an iterative process. And we do that until convergence. So, and I'm going to show you here the details. I know that it's maybe difficult to follow, but I just wanted to show you, I mean, first of all, when we do PGD, we end up with a lot of equations that we need to deal with. So I'm just trying to show you the systems that we obtain when we use a PGD. It's kind of involved, and I would like you to bear with me and try to follow. I'm trying to explain as clearly as possible the different results that we obtain. So here, lambda, we assume first that lambda is known. We have our test function, which is going to be lambda mu star. Mu star, basically the test function with respect to x. When we introduce this into our equations, this is what we obtain. And of course, the idea is now we have a problem in mu that depends only on x, because thanks to the separation of variable, we have our coefficient that we can evaluate. So we are going to have this here alpha, which is simply going to be the integral over time of lambda squared that we already know, and same for beta. And this is our second parameter. So basically here, and what we can do here, we obtain a lambda double dot that we can rewrite as such, introducing only simply the first derivative of lambda. So what is important is basically now we have a problem that we need to solve. It's a problem in 1D, and this is this classical problem that we will obtain if we didn't have time. Okay, so that's the first problem for the first iteration. And then once we'll get the first iterate, we are going to look for now lambda, considering that mu is known. And we do the same. We are, so the only thing is that Q star is going to be now, the test function Q star is going to be the product of mu, which is known, and lambda star, the test function with respect to time. And this is the problem that we are going to obtain. Again, it's a problem in time. And the coefficients can be computed easily using the solution mu. Okay, so here we have kappa. Basically, this is the term with respect to the rigidity, which is basically the K matrix that we obtained before, and sigma, the one with respect to the mass matrix. And we obtain, so now with this equation, we can do the discretization in time using Newmark as before, and we obtain for lambda a system that is very similar to the one we had I showed before in the case of the classical formulation for finite element formulation. Okay. Hey, don't hesitate to interrupt me or ask questions if something is not clear. All right. So again, in some sense, it's not that difficult to understand. It's more technical. We just use a fixed point approach. We iterate to compute lambda and mu for each mode Q that we are looking for. Now, there is one point I would like to make is that we can actually update the temporal modes. So we have computed this. We suppose, using the process that I just showed you, we are going to get this solution. One issue that we observe is that this lambda m and mu m are computed based on the information from the previous modes. But at this point, we accepted that the previous modes were okay, and we don't change them. However, the previous modes can also affect our solution lambda m and mu m. So we propose here to update those temporal modes. So what we do is we compute only globally all the temporal modes, and we don't care about the mu k. In doing that, we do get a better combination of the special modes. Okay. And I'm not going to show all the details of what it involves, but essentially we need to recompute we recompute all the lambda k. The thing is, this is a process that is, it seems time consuming, but actually it's pretty fast. All right. So that's actually, and I will show you with the results, that it's actually an important step for the solution of our problem. Okay, I'm going now to go through the PGD using the Hamiltonian formalism. And essentially, it's kind of a repeat of what I just said, but now we have the two equations that we need to consider. So it's, of course, going to be a little bit more involved. As before, we're going to proceed with a fixed point approach until convergence. So now what we are looking for is mu rho, knowing lambda and omega. And we do the same, but looking now for lambda and omega, and we iterate until convergence. Okay, so again, we just need to replace. So now we have our test function in terms of lambda and omega. Of course, that's the reason why we obtain a nonlinear system, and this is why we need to use a fixed point approach. This is the equation essentially that we need to solve with respect to space. So this is a 1D problem with all the coefficients that we are going to compute with respect to lambda and omega that we know. That gives us a system of two equations with the unknown mu, u with respect to mu, and the unknown with respect to nu. Okay. And once we have the modes in space, we look at the modes in time, doing the same thing. And what we observe is that we have terms like sigma comparable to the mass matrix, except that now we also have one integral without the density and one integral where it's 1 over rho, rather than what we had before, rho mu v. In that case, we can also use discretization in time to solve this problem. As before, we are going to use piecewise linear for the trial functions and constant for the test function. And this is the system that we obtain. This is a system, the system that is essentially very similar to the one we had earlier. We have the correspondence between kappa and the stiffness matrix and the sigma here that basically we had the mass matrix before. Okay, a point that I would like to make here is talking about the fixed point algorithm. And maybe this is one advantage we have with respect to the Hamiltonian formalism. Of course, we have to solve for two variables, but at the same time, we have some flexibility when we want to solve for the fixed point problem. The thing is, and this is something that we observe, I mean, Clément has observed essentially that we don't have simultaneous convergence with respect to Q and P. So the idea is to take advantage of the flexibility in this separated construction of the spatial and temporal modes in Q and P. If we observe that we have convergence on Q, then we can fix mu and lambda and solve simply for nu and omega until we have convergence of P. And vice versa, if we have convergence in the other variable, we do the opposite. So we can actually, and that's good also to gain time when we solve this fixed point problem. What we do also is an updating of the temporal modes for both Q and P, just as I described very briefly earlier in the case of the Lagrangian formalism. So I'm going to show some results. I just want to know. And the problem is that I had very beautiful movies, and I think it's going to be, I'm not going to be able to show them, but I'm going to start with a problem that I showed earlier, the one where we have a shock wave. So we are going to consider the same initial conditions. We have some external forces again 0. Here are the material properties that I'm using, and we use rho 7,000. Basically, and this is important because actually it's different from 1. And we saw that there is a difference between the Lagrangian and the Hamiltonian approach when rho is different from the unity. We have about, so we consider 224 elements in space and a time step, a very small time step. Okay, so the goal here is to compare the solutions that we are going to obtain with PGD using the two formalisms. in that case, we can compute also the errors with respect to the analytical solution. Okay.
Okay.
Yes.
I just wanted to say that we couldn't see actually the screen until just now. Now it updated. Before it was stuck on the previous slide, but just now I think it updated.
Oh, okay, okay. Okay, I didn't see it. Thank you. But it was only the last slide, right?
Yeah, just the last slide while you were discussing the numericals.
Okay.
This one.
Okay. So very briefly here, you have all the values that we are going to use for the first numerical solution, numerical problem. All right. So here I had some also beautiful movies. Let's try again. And it doesn't want to start. Okay. I don't know what happened. All right, so I'm going to try to describe what you were supposed to see. So this is the solution, the finite element solution. This is the solution with HPGD. In this case, the Lagrangian formulation give us more or less the same results at the PGD. What we would be able to observe here would be, that was the error between the solution, the exact solution, or the FEM solution and the LPGD. And the error, essentially, after many modes, were just concentrating around the front. But those were the error, basically, that we could expect. And in that case, for that case, the solution between the PGD and the HPGD and LPGD were very, very, very similar. Okay, so some details here. I'm showing, so the difference that we started to observe essentially is, so first of all, the error, the L2 error is very similar for the Hamiltonian and Lagrangian formulation. And we have a nice convergence. However, the error in the energy seemed to be larger for the Lagrangian approach than for the HPGD. And this is considering 223 modes. Here, the error is very much smaller than for the Lagrangian approach. In the updating process, also, what we started to observe is that the condition matrix that we would consider when we do this updating process, their behavior was very different. Here I'm showing the condition number of the matrix. So in red, it's going to be for the Hamiltonian approach, in blue for the Lagrangian approach. And at some point for the Lagrangian approach, first it would increase, and at some point it would even explode. And it's going to be clearer later, and you'll see the difference later that actually has some bad consequences. Now, with respect to time, what we see is that, so it's only the computational time. Basically, the HPGD was slightly cheaper, even if we solve for two different for two equations. And we have the double number of unknowns. It was still cheaper than the Lagrangian. Basically, this is during the fixed point iterations. HPGD was converging faster for the fixed point method, also because we could take advantage of this separation of the two modes, and we could actually converge maybe faster for one, and then accelerate then the convergence of the other. All right, that was the first case. Now I'm going to avoid essentially all those oscillations. I'm going to consider simply the case of a smooth solution. So in that case, initial conditions were taken as 0. Same for the external force. And we would consider a traction at the end of the bar. And this traction basically was given as a cosine function with respect to time. Same material properties, about the same number of time steps. And here we are going to, so we don't have, in that case, the exact solution or the analytical solution. So we would use overkill FEM solution. All right. And again, I had a movie, so I'm going to try to explain as best as I can. So here, I have the solution from the Lagrangian formalism and the one from the Hamiltonian formalism. And you see that after 63 modes, the solution looks very similar. Actually, we have more or less the same convergence for the L2 error. And here I'm showing the evolution of the total energy. So what was important to realize is that we would have apply the traction until a certain time t, and then apply 0 traction. So when we stop applying the traction, the energy would be constant. And this is what we obtain here. I'm going to show you again some results. So now we have with the 633 modes. I think I know that I was thinking about the movies. I think I know now what happened. So same L2 error, so with 633 modes, what we observe essentially again is that the absolute error in the energy is going to be smaller for the Hamiltonian in red. In blue, actually, we have still, after we stop applying the traction, we still have some oscillations. And for this problem, again, we see that the condition number, kappa, has a bad behavior for the matrix with respect to the Lagrangian. What is amazing is that for the Hamiltonian, the condition number remains always the same and close to 1. So that would be perfect. I'm showing now the solution when we consider 223 modes. And this is what happened. Basically, the condition number in the case of the Lagrangian approach behaves so badly that we don't get the solution. It diverges. We stop getting the solution after about 60, 65 modes. Concerning the Hamiltonian, no problem. We keep going. And even with 223 modes, we have a good behavior, and the error in the energy is very small. Concerning, of course, the computational time, as we introduce more modes, of course, the cost is going to be higher. But here we are really testing the method with many, many modes. In reality, in practice, what we would do is to have to be able to use only 10 or 20 modes. Okay, I'm going to show now a case. So we did also the same exercise with the damping. So we are going to introduce damping in terms of chi mu u dot. When we use the Lagrangian formalism, the only difference is that now we have this new term in the equation. When we use the Hamiltonian formalism, we have this new term here. So here there is a choice that we could make, is to say that we can distribute, actually we could replace the q dot by P actually doesn't change anything. Whether we keep Q dot or we have even a combination of Q dot and P, that does not change anything in the results. Here are the results. So I'm going to show now with 68 modes. The result, LPGD, HPGD, just fine until 68 modes, exactly the same. The error follows the same rate, more or less, and the total energy is well captured. No problem with that. Again, so now remember when we had no damping, we stopped the Lagrangian approach starting to get bad at 65 modes. Basically, what I would like to show here is we postpone a little bit the bad behavior of the Lagrangian approach, but eventually it's going to also behave badly. So again, this is the case of when we have 68 modes. Condition number start to get bad, and right after 68 modes, what's going to happen is the condition number explodes and we don't get the solution with the Lagrangian approach. Hamiltonian, no problem. So was it simply a problem with this updating process? Because actually the problem of these condition numbers exploding was when we were applying this updating process. The point of view, I mean, the thing is, if we don't do this update, we get pretty bad results. And so that stage was really important in order to get decent results. What we see here, without the update for the LPGD, we don't get the correct solution. For HPGD, better. I mean, when we look at those results, they are really very much comparable to what we should observe. However, the error is not as good as before. For the total energy, what we observe essentially is that the Hamiltonian approach does follow what we should observe. For the Lagrangian approach, it's, I mean, basically we cannot do it without this updating process. Okay, so some few remarks.
If I
Yes.
may ask you, then what is it that motivates this this explosion intuitively?
It's basically when we, okay, I need to go. Okay, that's. I think Clément will be able to answer your question.
Do you want me to answer right now?
Yes,
or later?
yeah. No, answer the question now.
Okay. Actually, when we use the approach with the Lagrangian, something that we didn't say, but we do, we ortho-normalize with a Gram-Schmidt algorithm. And with the Lagrangian, we have to make a choice whether we ortho-normalize our spatial mode accordingly to A or accordingly to B, AX and BX on the graph. But with a Serge? Ah, yeah. Okay, thanks.
Yeah, sorry.
So the choice we made, we orthogonalize our mode accordingly to B. But since the matrix MT AX M is not like, yeah, also this matrix M that you see there, you have to see it as if it was the spatial modes that were in color victims, vectors, okay? And the matrix M transposed BXM is supposed to be the identity, actually, since we use the Gram-Schmidt algorithm to orthogonalize the spatial mode accordingly to B. But in the end, the matrix M transposed AXM won't be the identity.
Just one question. Are you using the Gram-Schmidt or the modified Gram-Schmidt?
This is a kind of a modified Gram-Schmidt because we have to update also the temporal modes. It's like if you update the spatial modes, it will have an impact on the temporal modes too.
No, I was mentioning that there are two algorithms, right? Gram-Schmidt and modified Gram-Schmidt. And I think modified Gram-Schmidt is made for stability.
Sorry?
I was asking if you were using the modified Gram-Schmidt or the Gram-Schmidt to orthogonalize.
Oh, no, it's just a simple Gram-Schmidt.
I think that's unstable.
Although you think that's the reason why we observe?
It could be. I'm not saying that that is the reason, but that is why the modified Gram-Schmidt was created.
Okay. So this is something that, okay, we will look at.
Just one more question. You said one possibility to enhance this was to actually, once you have the modes, right, you fix the space and you enhance the time and then you iterate backwards. Is it possible to also do some kind of, I mean, once you get to the number of modes that you want, say, try to do some kind of Gauss-Seidel where you actually keep all modes except one and you try to enhance that given the others that are fixed or something like that? I mean, that you could work in blocks or something like that?
We could do that. What we saw actually, what was important was essentially to just to update the temporal modes. Cool. But I think that could be a possibility to look at. What I mean at this point, the thing is, what we see is most of the time the Hamiltonian approach gives us better results. Actually, the thing is, basically, since we have also two different variables to play with, we have more flexibility for the fixed point iteration and for other things. So those are my some remarks here that I would like to make. Of course, when we use the Lagrangian formalism, the systems would be easier, the system of equations is easier to manipulate. We have only one equation. What we have observed at this point, and maybe there are ways to improve this, we see the degenerations of some of the matrices, and of course, the lack of convergence in certain cases. With the Hamiltonian formalism, it's then way more stable. Of course, we have twice as many degrees of freedom, but actually it doesn't affect the computational time. It's nice because actually we have a systematic derivation of the discrete system, and we have also some flexibility when we want to use some numerical approximation, especially in time. And also for us, because in the end, what we want to do is to look at the error and essentially try to develop a method that is going to be optimized with respect to some error in some quantities of interest. We have then the possibility of formulating the problem as a minimization problem. And the idea is as follows. I think it's essentially that if we have a quantity of interest, the idea would be to now pose the problem as looking for Q and P, which minimize essentially our action, but now subjected to some constraint on the quantity of interest in order to satisfy some accuracy. And the idea would be to follow what we did earlier with Kenan Kergren, Ludovic Chamois, and Marc Laforêt, where we presented a goal-oriented version of the PGD method. This is something that we were really much after. And that's what the next step of this work will be. So what I presented today, to conclude, I showed how to construct some reduced order models of the wave equation based on the Hamiltonian formalism. The good thing about this formalism, it provides us with a symplectic discretization of the problem. We do observe a conservation of the energy. We had more problems with the Lagrangian approach. This is what I just said. I think this is the suitable framework when we want to use a method for adaptively constructing PGD models. And of course, the idea next is to extend these ideas to parametric PDE. So we would do in that case separation with respect also to the parameters in order to be able to use. Thank you very much, and I would like